Hello, everyone. My name is Raja, and today I'm going to talk to you about a new technique we've developed for diagnosing the source of performance changes in distributed systems. This is joint work with many people from Carnegie Mellon, Microsoft Research, and Google. So we all know that diagnosing the source of a performance problem in a distributed system is very time-consuming and difficult. And this is because the problem might be in one of many different components, subcomponents, or functions. Worse, the problem might not be due to a single component, but rather might be due to interactions between them. And so what we clearly need are tools to automatically localize the source of problems to just the relevant areas. Request flow comparison is a technique we've developed for automatically localizing the source of performance changes. It relies on the key insight that such changes often manifest as changes in the flow of requests through the distributed system, for example, the components they visit, the functions they execute, and so on, or in their timing. Explaining these differences and showing how they differ from previous behavior can significantly localize the source of the problem and focus developer efforts. More concrete, I want to describe my experiences debugging the performance of a feature addition to a distributed storage service and show how our technique of request flow comparison could be used to quickly localize the root cause. The system is composed of many clients, NFS servers, metadata servers, and storage nodes. But for this talk, I want to concentrate on the case where there's only one of each and two storage nodes. So in this system, to request data for a file, clients must first send a request to the NFS server. The NFS server must look up the location of that file in the storage nodes and permissions at the metadata server. The metadata server itself might incur storage node access to look up this data. Once the NFS server has received the location of the file and the permissions, it's free to access the storage nodes directly and respond to the client. So the key thing to notice here is that every single file access requires a metadata server access and hence a network round trip. And so you can imagine why this might be a performance bottleneck for really small file workloads. The feature we added was to have the metadata server prefetch extra metadata to clients on every request. So in cases where the NFS server missed in its metadata cache and had to access the metadata server, the metadata server returned additional related metadata in hopes of squashing future accesses, increasing the cache hit rate, reducing the number of network round trips, and hence increasing performance. So this is great, right? So you see here in the common case, the client sends a request to the NFS server, and the NFS server is able to access the storage nodes directly and respond to the clients. So once we added this feature, we were really happy. But amusingly, we found that adding this prefetching functionality didn't improve performance. Rather, it reduced it. And so the question is, how would one go about officially diagnosing such a problem? Request flow comparison would show the changed behavior in the problem period, the mutation. That is, you would see that certain requests that access the metadata server incurred many repeated database lock accesses, several levels of abstraction below where the prefetching functionality was added. So you see here in this graph, different colors represent the different components accessed by this request. And the orange nodes show the metadata database locks that we observed. It would show that the same request before the prefetching functionality was added, that is, the mutation's precursor, incurred many fewer repeated database accesses. Comparing the mutation to its precursor localizes the source of the problem, specifically these extra database accesses. With this extra intuition, perhaps a developer could realize that the problem was due to the fact that the extra cost of these database accesses outweighed the extra savings due to cache hits. So once again, we see here the root cause of the problem here is localized by showing how the mutation, the flow during the problem period when prefetching was enabled, differs from the precursor, the path to the same request before the prefetching functionality was enabled. So our approach of comparing request flows identifies distribution changes in request flow timing and structure. As such, it is distinct from anomaly detection tools, for example, Magpie and Pinpoint, where request flow comparison attempts to identify key steady-state changes in request flows between two periods Anomaly detection tools attempt to identify rare requests that differ greatly from others within a single period. So though request flow comparison can't be used to diagnose all sorts of problems, for example, why performance has always been slow, it does have many use cases. For example, diagnosing the root cause of performance regressions, comparing request flows between after regression to before the regression to understand why performance has changed. It can also be used to diagnose performance degradations within a single execution of a system. For example, by comparing the last 1,000 requests observed to the first 1,000 to understand why the last 1,000 are so much slower. Right. A final interesting use case is that request flow comparison can be used to eliminate the distributed system as the culprit. By comparing two periods of behavior and showing that nothing within the distributed system has changed, one can eliminate the distributed system as the potential problem, as the contributed root cause, and focus developer effort on other external factors. Our paper presents several contributions. I'm going to focus only on a subset here, specifically heuristics and algorithms for identifying mutations, precursors, and for ranking them according to their contribution to the performance change, their implementation in a tool set called spectroscope, and the use of spectroscope to diagnose real, previously unsolved problems in a distributed storage service called Ursa Minor, which looks identical to the architecture diagram I showed you in slide 3. Also to show that our approach is valid in other systems, preliminary experiences using spectroscope to diagnose real problems within select Google services, for example, Bigtable. So in this slide, I'm going to show you the spectroscope workflow. I'm going to actually animate each step in to show you what each step does. And then I'm going to use this slide as my outline slide for the rest of this talk. Spectroscope takes as input request flow graphs from a problem period and a non-problem period. It bins similar requests into categories and uses these as a fundamental unit for comparing request flows. Using statistical tests and various other heuristics, it identifies those categories that contain mutations. We consider it two types, response time mutations and structural mutations. Next, it ranks the categories that contain mutations according to their effect on the performance change. And finally, it presents the results to the user in a UI. So in the next section, I'm going to walk through each of the elements of this workflow, describe the algorithms and heuristics we use, and explain our rationale for choosing them. In general, we favor simplicity and those that regulate false positives, because those are perhaps the worst failure modes of such automation tools, because of the amount of developer effort that's wasted. All right, so first I'll explain how we obtain the request flow graphs. To obtain request flow graphs, we leverage end-to-end tracing techniques, which capture the control flow of individual requests as they travel through the components of a distributed system in detail. It has been described extensively in previous research, for example, Stardust, Xtrace, and Magpie, and is now used in production systems, for example, in Google data centers. It works as follows. Trace points are either manually or automatically inserted in important areas of the distributed system software. Often they're automatically inserted at the component boundaries by a common RPC mechanism, and developers are responsible for adding trace points within various other areas of the system themselves at key points of interest. Right. During runtime, the tracing mechanism assigns an ID to each request that allows it to track the trace points accessed by individual requests. Later, this ID can be used to stitch together the trace points accessed by each request to construct request flow graphs. Right. One key thing to note about these request flow graphs is that their granularity is limited by the number of trace points. So if two requests execute different functions, but there's no instrumentation within those functions, the request flow graphs generated for them would look identical. Right? They wouldn't be able to distinguish between these two requests that truly did execute two different functions. Using request sampling, in which a decision is made at the entry point of the system whether or not to collect instrumentation for an entire request, the overhead of end-to-end tracing can be reduced significantly. For example, it's often less than 1% in many systems. Here's an example for a striped read operation in Ursa Minor. For illustrative purposes, this data is striped only over 2 nodes. So the request would enter the system and would execute an NFS read call trace point, and that information would be logged in the request flow graphs. Next, this request would travel to the NFS cache component, and in this case, it misses an NFS cache. We see that it takes about 100 microseconds for a request to travel from the entry point of the system to the cache component. Next, the NFS server would execute 2 concurrent read requests to each of the storage nodes on which the data is striped. And we see that executing these RPCs takes about 10 microseconds. And then in the graph, you would see some work done on each of the storage nodes. In a real request flow graph, additional trace points will be generated within each of these storage nodes. But I'm not showing them here just to make sure things fit on a single PowerPoint slide. Right? So the work on storage node 1 finishes first. And we see that the storage node 1 replies. The network time for reply is about 1.5 milliseconds. So there's a really slow network. Right? Sometime later, we see the second storage node replies. And this information is logged in the request flow graph. And this also takes about 1.5 milliseconds. Finally, when the NFS server has all the data it needs to return data to the client, it acts as one final instrumentation point saying that it's done, as seen by NFS reply node, and then returns to the client. The request flow graph will also show the overall response time of this request, which is about 8 milliseconds. And that's dominated by the rightmost subpath of this graph, the critical path. So the key takeaway of this slide is simply that the nodes show the trace points accessed by individual requests, and edges show latencies. All right. So to summarize, so far I've shown how we obtain request flow graphs. The next step of Spectroscope's workflow involves grouping similar request flow graphs into categories. All right. So categorization is necessary because it's both meaningless and infeasible to compare individual request flows. It's infeasible because even small distributed systems can generate thousands of requests per minute. And it's meaningless because we need to define some valid axes of similarity that we expect to be similar between the both periods we're comparing in order to find relevant differences. Right? So this categorization step groups together similar request flows and uses these as the basic unit for comparisons. And this allows us to identify mutations by comparing the distribution of various statistics within these categories. In choosing what to bin into a single category, we choose to bin identically structured requests into the same category. And this uses a very informal expectation, common especially in distributed storage, that requests that take the same path through the distributed system, access the same components, execute the same functions, have the same amount of parallelism, should incur similar costs, for example, response times. This isn't a new expectation I'm making up. It's actually commonly used. For example, many systems have different counters for reads, writes, and attribute requests in distributed storage. And this is because these requests are serviced very differently, and they essentially take different paths to the system. I'm just formalizing a bit more here. We evaluated the validity of our same path, similar cost expectation in Ursa Minor and in Bigtable. We found that in Ursa Minor, 88 to 99% of categories generated for 3 workloads satisfied this expectation. That is, they had low intra-category variance of response times. For Bigtable, we found that 47 to 69% satisfied expectation in 3 different data centers that we looked at. So this lower value that we see for Bigtable occurs for 2 reasons. First, there's simply less trace points in Google's tracing mechanism. Right? So often for Bigtable, you would see the underlying type of the request being issued, for example, a Bigtable read or a Bigtable mutate. And then you would see whether or not this generated an underlying GFS request. And so what's happening is that many requests that take truly different paths through the distributed system are being merged together into the same category. Right? Additional instrumentation would serve to disambiguate these truly unique paths and would increase this number. The second reason is that there's simply more contention in Bigtable than Ursa Minor. And so this obviously increases the amount of variance that you see for response times. This is interesting in that it implies that this process of categorization can essentially be used to localize problematic sources of variance. For example, and help developers reduce it or perhaps eliminate it when possible. This would help the quality of automation tools, such as Spectroscope, that rely on predictability to function, and would also help quality of service by reducing end-user visible variance. All right, so the next step, I'm going to talk about how we identify mutations, both response time mutations and structural mutations, and then how we rank them according to their contribution to the overall performance change. All right, so we consider 2 types of mutations. The first are response time mutations. These are basically timing changes. They're requests that are structurally identical in both periods. They access the same components, execute the same functions, and so on, but they simply have larger problem period response times. And to help diagnose problems that manifest as this type of mutation, Spectroscope automatically localizes the root cause by identifying the interactions responsible for this timing change. So when comparing request flows to identify mutations, we can't expect these response times to be exactly identical between both periods. There will always be some natural variance in timings, right? So a key challenge is to separate natural variance in timings from true mutations or distribution changes. To do this, spectroscope uses standard hypothesis tests. So these tests take as input two distributions and determine whether there's enough evidence to reject the hypothesis that both distributions are essentially the same. If there is enough evidence to yield a false positive rate of less than a certain value, the distributions are claimed different. The advantage of using a hypothesis test, of course, is that over a raw threshold, is that it guarantees a maximum false positive rate. In order to identify the interactions responsible for response time mutation, once we identified categories that contain these mutations, we simply run these same statistical tests on each of the edge latency distributions of the request flow graphs. So here's an example of identifying categories that contain these mutations. Here you see one category, and you see in the dotted line the response times of requests assigned to this category from the problem period. The solid line shows you the distribution response times assigned to this category from the non-problem period. You can see that these two distributions are really different. They have different means, and the variance around their means is very small. And so the hypothesis test will have enough evidence to reject the hypothesis that both distributions are the same. And so we will identify this category as containing mutations. The second category is very different. You see that the response time distributions from both periods are really similar in their means, and their variance is very large. So in this case, the hypothesis test will not have enough evidence to claim that distributions are really different, and so we will not identify these as containing response time mutations. Here's an example of response time mutation. Here we see a read request that accesses a storage node. It takes about 1 millisecond in the problem period, and requests that take this path in the non-problem period incur about 110 microseconds latency. And so to identify the interaction responsible for this timing change, we would iterate through each of the edges and apply the same hypothesis test. And we would identify the work done in storage node 2 as the one responsible for this mutation. So once again, we see that the problem is essentially localized by identifying the interactions responsible for this timing change. The second type of mutation we consider are structural mutations. These are requests that take different paths in the problem period as opposed to the non-problem period. That is, they execute different functions, access different components, and so on. The root cause of these mutations can be localized by identifying their precursors or their most likely path during the non-problem period and showing how the mutation and the precursor differ. So for example, the metadata prefetching problem I described earlier in this talk, for this problem, structural mutations would correspond to requests that accessed the metadata server and incurred many repeated database lock accesses. Their precursors would be requests to also access the metadata server, which incurred many fewer database lock accesses. Another example of a structural mutation precursor pair might be requests that now must retrieve data from a far-off data center in Asia, whereas previously they were able to retrieve the same data from a close-by data center in the US. To identify categories that contain structural mutations, we assume a similar workflow is executed in both periods. And so this essentially means that categories that contain more problem period requests must contain structural mutations because those requests must have come somewhere. They must have mutated from some other category. Conversely, requests that contain less problem period requests than non-problem period requests must be precursor categories because these are categories that must have donated requests. In this case, in order to differentiate natural variance in counts from true distribution changes, we end up using a raw threshold. Once a complete set of mutations and precursors have been identified, we still have the problem of identifying which precursors are likely to have donated requests to which structural mutation categories during the problem period. This is accomplished via a combination of 3 different heuristics. I'm not going to go into detail about these heuristics here. They're completely described in the paper. But they use the 3 attributes shown in the picture on the screen. Specifically, they use the high-level type of the request, read, write, and so on. They use the number of requests assigned to each category from both periods. Here, NP means the number of requests assigned to the category for the non-problem period. And P refers to the number of requests assigned to that category from the problem period. And finally, uses the structural similarity between requests in the categories. Once again, our paper contains the complete details for how we accomplish this. Here's an example of a structural mutation category. You see the mutation on the right-hand side, and you see that these are requests from the metadata prefetching problem that access the database lock many more times. And you see its corresponding precursor, the path of that request during the non-problem period before prefetching was enabled, where the database lock was accessed many fewer times. So once again, a root cause of structural mutations is localized by showing how the mutation and the precursor differ. Finally, we have to rank categories according to their contribution to the performance change. This is necessary for two reasons, right? First, there may be more than one problem, and so you want to focus developer effort on the ones that will yield the most benefit. Second, one problem might yield many different mutations. So to give you an example of this, consider a bug in a cache that causes more requests to miss in that cache during the problem period. In this case, some requests will miss in that cache and hit in the next level cache, and so that's one mutation. Because that next level cache is more loaded and more utilized, some requests might start missing in that cache too. And so you see that one problem has generated two different mutations. And so in such cases, we want to focus diagnosis effort on the categories or on the mutations that affect performance the most. Our ranking scheme is very simple. It's simply based on the number of requests affected times the delta in response time. So for structural mutations, this would be a number of extra requests in the problem period times the change in response time between that category and its precursor category. For response time mutations, this would be the number of non-problem period requests times the change in response time within that category between the non-problem period and the problem period. All right, finally, I'd like to give you a quick mock-up of the UI layer for this tool. All right, so in the UI layer, you see a ranked list of the categories containing mutations, and the developer can click on any of these categories. He might decide to investigate the highest ranked one first. In this case, there's a structural mutation category, and it will show you both the structural mutation and its precursor, and the developer could look at it to understand how these differ in order to localize root cause. If he decides this isn't relevant to helping him solve the problem, he might decide to investigate a lower ranked category next, in this case, a response time mutation category. In this case, we would simply show you the mutation, and we would highlight the interaction responsible for the response time change in red. All right, so before I conclude, I want to talk about two case studies of applying spectroscope to diagnose real problems in Ursa Minor in Google. So our Ursa Minor case studies, we use spectroscope to diagnose real performance problems in Ursa Minor. 4 of them were previously unsolved real problems. And to get a sense of the quality of spectroscope's output, we evaluated its ranked list by measuring 2 metrics. First, the percentage of top 10 results that are relevant. So this is important because developers will naturally investigate the highest ranked results first. It's kind of like searching on Google. Second, the percentage of total results that are relevant. This is an indication of the overall quality of spectroscope's output. You see that our results were mostly good. In the best case, for the configuration problem shown. Sorry, let me explain what this graph shows first. You see on the x-axis the different problems that we diagnosed. It's not important to understand their names, just that they're different unique problems. And the yellow bar shows the percentage of top 10 results that were relevant, and the blue bar shows the percentage of total results that were relevant. And so you see that in the best case, 98% for the config problem, 100% of all results, the top 10 results were relevant, and 98% of all results were relevant. The worst case result was the create problem, for which 40% of the top 10 results were relevant, and 36% of all results were relevant. But the highest ranked mutation was one that was relevant to helping us diagnose the problem. So I already described to you the prefetching problem. That was the example I showed you at the very beginning of this talk. And next, I'd like to explain to you the configuration problem to give you an idea of how spectroscope can be used a bit more. All of our case studies use the standard 5-component configuration of Ursa Minor. That is, one client, one NFS server, one metadata server, and 2 storage nodes. Metadata is stored on one of the storage nodes, and data is stored on another storage node. This is the configuration that's used for Ursa Minor's nightly regression tests, which is perhaps the best use case for spectroscope because it lends itself to very well-defined problem periods and non-problem periods. All right, so for this problem here, we observed a slowdown in key benchmarks after a large code merge. And so we were curious to understand what was going on. All right. We applied spectroscope to compare the request flows generated after the code merge to those generated before the code merge. And we saw that the output revealed many structural mutations. Right? The highest ranked ones were all structural mutations. And he found that these mutations and precursors differed only in the storage node accessed. In the problem period, the metadata server was writing and reading data from the data storage node instead of its own metadata storage node. Whereas in the non-problem period, both storage nodes were being used. The extra load on the data storage node was slowing down the system. So this is great. We've localized the bug to an unexpected interaction between the metadata server and the data storage node. But it's still not clear what the root cause is, right? So what's going on? So we thought the mutations might be caused by change in some low-level parameters being sent to the system. For example, perhaps a client was simply saying that to just write data to just one storage node, right? Perhaps there was some difference in the RPC parameters that were being sent. And so we used another functionality of spectroscope that I haven't described, I'm going to quickly talk about now, that lets us pick a mutation category and a precursor category and essentially identify the low-level parameters that best separate the two, right? Doing so immediately showed differences in encoding parameters. For example, it had a fault tolerance scheme specified and so on. This localized the root cause to one of two configuration files. And this turned out to be a true root cause. It was an inadvertent change to obscure configuration file that was almost never changed. It had been changed by mistake as part of this commit, but wasn't actually part of the commit. All right, I want to quickly do one more problem here. So it'll take about a minute, and then I'll conclude. All right, so at Google, there's one example of diagnosing a problem at Google. So developers of a distributed service at Google were running load tests on their distributed service in two different data centers. And they really expected the performance to be similar in these two data centers. But in fact, they found the performance to be very different. And they're curious as to whether this was a problem with their distributed service or whether it was a more pervasive problem. By comparing request flows generated between the two data centers, we saw that there were many mutations. Most of them are response time mutations, so they're all timing changes. Trying to identify the interactions responsible for these changes, we found changes not only within the distributed services software, but also in network time and in the time taken to execute certain dependencies, for example, big table accesses. So this led us to suspect the root cause was not due to the service itself, but rather due to an issue with the slower load test data center itself. This was, in fact, the root cause. It turns out the shared big table in the slower load test cluster was basically hosed, wasn't working properly, and this is what was causing the slower performance. So this is an example of using request flow comparisons to rule out the distributed service as the root cause and focus developer effort on other external factors. All right, so I'm done. I want to quickly summarize. I introduced request flow comparison as a new way to diagnose performance changes in distributed systems. I presented algorithms for localizing problems by identifying mutations, precursors, and ranking them according to their contributions to performance change. And I showed the utility of our approach by using it to diagnose real unsolved problems within Ursa Minor and Google. Our paper contains many more examples of applying spectroscope. Thank you.